Welcome back, young physicists. Have you ever wondered why, when you press your finger against a water balloon, you feel a gentle push back from every direction inside? Well, that's the magic of pressure in fluids. Now, here's a little joke to kick things off. Why did the fluid break up with the solid? Because it felt too pressured. Alright, now, pressure in fluids is essentially the force pressing normally, or at a right angle, against a surface divided by the area over which this force acts. Imagine lots of fluid molecules bumping into that surface. Their tiny impacts are constantly transferring momentum, and that adds up to what we call pressure. Mathematically, pressure equals force divided by area, with force being the normal force acting perpendicular to the surface and area being the surface area itself. One important thing to note is that in fluids at rest, pressure is equal in all directions at a given point, which is known as Pascal's law. Picture yourself diving into a calm pool, the water's pushing you equally from all sides. Also, since fluids can be compressed, their pressure can change depending on how deep you go and how dense the fluid is, as well as external conditions like temperature or additional forces. That's why deep-sea explorers face such enormous pressures down below. The fluid is literally pressing in from every side. Let's continue our underwater adventure. Imagine you're swimming down into a lake. Have you noticed how the deeper you go, the more your ears pop? That's because the pressure in the water increases as you dive deeper. This increase in pressure at a point beneath a fluid's free surface happens because the water above is weighing down on you. Now, think of a fluid column, like a tall glass filled with water. The pressure at the bottom has to balance the weight of all that water above it. Scientists express this with a neat formula. The pressure at depth equals the surface pressure plus fluid density times gravitational acceleration times the height of the fluid column above. Put in words, pressure at a depth h equals surface pressure plus rho times g times h, where rho is fluid density, g is gravity, and h is depth. This formula assumes the fluid can't be compressed and that gravity remains the same, pretty accurate for small depths like swimming pools but might vary for deeper oceans. Plus, pressure at a point underwater acts the same in every direction, just like an invisible force field wrapping around you evenly, so your ears really get equal pressure from all sides. Now, before we dive deeper, let's clarify something that confuses many students: absolute pressure versus gauge pressure. Imagine you're measuring tire pressure on your bike. Your pressure gauge doesn't give you the total pressure from absolute zero. It actually shows pressure relative to the atmospheric pressure outside. Absolute pressure is the total pressure measured starting from a perfect vacuum, so it includes the atmospheric pressure pressing on us all the time. Gauge pressure, on the other hand, is absolute pressure minus atmospheric pressure. If the gauge reads 0, that means the fluid inside is at atmospheric pressure. If it reads negative, you're in a vacuum zone where pressure is less than what the atmosphere pushes. So, typical instruments like pressure gauges measure gauge pressure, helping us find out if a tire is overinflated or underinflated relative to the air around us. This distinction helps engineers, divers, and even weather forecasters to interpret pressure readings correctly. Pressure sounds complicated, but when it comes to units, it's quite straightforward. In the International System of Units, we measure pressure in pascals, abbreviated as Pa. 1 Pascal is 1 Newton of force applied over 1 square meter of area. Simple, right? So, pressure equals force divided by area, measured in newtons per square meter. Remember, newtons come from mass times acceleration, that's kilograms times meters per second squared. This means the dimensional formula for pressure is mass times length to the power of -1 times time to the power of -2. Don't worry if that sounds fancy. It just means the property comes from these basic quantities. Other units like bars and atmospheres are also used. 1 bar equals 100,000 pascals, a handy number when talking about tire pressures or engine loads. 1 atmosphere, the air pressure at sea level, is approximately 1.013 times 10 to the 5 pascals. Dimensional analysis like this helps physicists ensure formulas make sense and units remain consistent in all calculations, preventing silly mistakes. Picture this. You have two straws of equal length, one filled with water and the other with mercury. If you were to measure the pressure at the bottom of each, you'd notice something interesting. Hydrostatic pressure depends on three main factors: the fluid's density, the gravitational acceleration, and the height of the fluid column. According to our trusty formula, pressure increases linearly with depth. The deeper you go, the more pressure you feel. But here's the twist: mercury is about 13 times denser than water. So, even a small column of mercury creates much more pressure than the same height of water. That's why mercury is used in barometers for measuring atmospheric pressure. Also, oddly enough, the shape or area of the container holding the fluid does not affect the pressure at a certain depth. This is called the hydrostatic paradox. So, whether it's a wide tank or a narrow tube, pressure depends only on depth and fluid properties, not container shape. Let's get our hands a bit more mathematical. Imagine a tiny rectangular element of fluid with area A and very small thickness dH, submerged in a fluid at rest. This element experiences pressure from above and below. Balancing the vertical forces, pressure times area at the top plus a tiny change in pressure times area over thickness dH equals the pressure at the bottom plus the weight of the fluid element. If we rewrite this relationship, the change in pressure with respect to depth dH equals negative rho times g. Breaking down the math, this means the pressure decreases as we move up by an infinitesimal distance dH. Integrating this differential equation from the surface, where pressure is P0, our starting pressure, down to depth h gives pressure equals surface pressure plus rho multiplied by g multiplied by h. That's exactly our earlier formula but derived from fundamental force balance, physics in action. Imagine a graph with depth h on the horizontal axis and pressure P on the vertical axis. In a static fluid like water, pressure increases linearly with depth, so the graph is a straight line starting from the surface pressure at zero depth. The slope of this line is fluid density times gravitational acceleration, rho times g, and the line crosses the y-axis at P0, the surface pressure. This simple linear relationship is very practical. Engineers use it to design manometers, devices that measure pressure differences using fluid columns. The manometer's fluid level moves up or down based on pressure changes, thanks to this exact pressure-depth connection. This relationship holds well for incompressible fluids such as water, under stable temperature and gravitational fields, helping us predict pressure in everything from dams to deep-sea submarines. Alright, time for a quick calculation. Suppose we want to find the pressure at 5 meters depth in water. We know water's density is 1000 kilograms per cubic meter, gravitational acceleration is 9.8 meters per second squared, and atmospheric pressure at the surface is about 1.013 times 10 to the 5 pascals. Using our formula, pressure equals surface pressure plus density times gravity times depth. Substituting, we get 1.013 times 10 to the 5 plus 1000 times 9.8 times 5. Calculating, that's 1.013 times 10 to the 5 plus 49,000, giving 1.503 times 10 to the 5 pascals total pressure at that depth. This value makes perfect sense as pressure increases with depth due to the weight of the water above. So your ears really do feel that squeeze. To wrap up, Pressure in fluids is the normal force divided by area, a simple yet powerful concept. It acts equally in all directions inside static fluids and rises linearly with depth according to surface pressure plus fluid density times gravity times height. Remember, gauge pressure is what we read relative to atmospheric pressure, useful in everyday tools like tire gauges, and can even be negative to indicate vacuum conditions. The C unit is the Pascal, based on newtons per square meter, with related units like bar and atmosphere also common. Dimensional formulae ensure our calculations stay consistent. Understanding pressure differences explains why fluids move, how submerged objects feel forces, and lays the foundation for hydrostatics. Pressure isn't just a physics term, it's all around us, helping things work smoothly, from hydraulic lifts to ocean depths. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.